Hello everyone. In the last video, we talked about data arrival time and data required time, and we came to a conclusion that the data arrival time should be less than data required time for the system to work at 1 nanoseconds or at a clock frequency of 1 gigahertz. So we made all these conclusions in the last video. So let us try to look into how does the delta values or the values of the clock network propagated delay actually affects this particular equation, and how can it make the system go bad, or how can it make the system go work beyond 1 nanosecond or less than 1 gigahertz. So let's look into that first. So there is a definition of slack, and the slack is the data required time minus data arrival time. So it's something like this. The arrival time is this much. You arrived at this time. Then you're supposed to come at this time. So whatever difference between the data required time minus the data arrival time becomes the slack. So if it is positive, we are good because we expect data required time to be greater than data arrival time. So basically, we don't expect the arrival time to go beyond data required time. We don't expect anything to be late over here. So it's as simple as that. As we don't expect anyone to be late in a meeting, we don't expect anyone to be late even while the data is coming. So when the data is coming, it should not be late. So if it is not late, the slack will be positive, or the data can arrive exactly at same time. So the slack could be 0. So it should be positive or 0. If it is negative, it means that your data arrived at a late time, than at a time which is beyond data required time. So it arrived late. It's as simple as that. So basically the person is late for his meeting. And by how much time he is late, that is called as a negative slack, and that is a slack that is being that we have to worry about. So let us see what all things can affect the slack. What all things can make the slack as negative. Okay, what all things can go wrong? So first of all, theta, the combinational delay over here, this particular combinational delay can be very bad. That if this combinational delay increases, there is a chance that the term on the left hand side can be greater than the term on the right hand side, and we get a negative slack. That is one reason. And second important reason is the delta 1, that is the clock network propagated delay for the launch flop. If delta 1 goes on increasing, indefinitely, so there should be way to control this. If it goes on increasing indefinitely, you see how the left hand side of the equation gets affected, and as a result of that, the data arrival time gets affected. Basically it gets increased, it becomes more and more late, and as it becomes more and more late, you tend to see a negative slack. Let's see that. So for example, let us take a case where we added one buffer in the launch clock path delay with a delay of x. Okay, so the left hand side of the equation becomes theta plus delta 1 plus x. So now the data arrival time, let's quickly go to the previous slide. So the data arrival time, which was theta plus delta 1, now the data arrival time becomes even more. Basically it becomes theta plus delta 1 plus x. And now this data arrival time has to be less than this data required time, this complete data required time. Basically, you have put a speed breaker in the path. So once you put a speed breaker in the path, you still have to arrive at a time which is less than the required time. You still have to arrive on the meeting at the right time. It's as simple as that. So this equation, if you see it on the left hand side, you're expected to be less than the data required time, but addition of this particular buffer might get you late over here. So if you see, if you increase this particular term, if you increase more and more buffers over here, how your left hand side can go beyond right hand side, and you tend to see a negative slack. Let's see how do we do that. So let's say we are adding one more buffer with a delay of x. So your left hand side delay again increases. It increases by 2x. So it was theta plus delta 1. Now it has increased to theta plus delta 1 plus 2x. So left hand side, more and more you try to introduce delays in the left hand side, the more is the possibility that it might go beyond the data required time, and your data required time minus data arrival time becomes negative. So it's as simple as that. If a person has to attend a meeting at 7 p.m. and you try to put, and at 7 p.m. is the data required time, and if you try to put more and more obstacles on his path, he will tend to get late, and the amount of time that he gets late, that is, if he arrives at 7:20 p.m., he's late by 20 minutes. So that is the slack. That is a negative 20 minutes, and that is the slack. Similarly, you tend to add more and more obstructions in the clock path. The data arrival time, the time that is required for the data to reach at this point, goes beyond the required time, goes beyond the time that it is required to reach at this point, and you end up with a negative slack over here, which is bad for a design. So if that is the case, what will happen is, if you can't commit that the system will actually work at 1 nanoseconds or at 1 gigahertz. It might, if the data arrival time goes beyond the data required time, then the clock frequency that we are expecting to be 1 gigahertz, which will be running slower. It will be basically the clock period will not be 1 nanosecond. It might increase to 1.5 nanoseconds or something, and the inverse of that will be obviously less than 1 gigahertz. So basically we have to reach this. That is the final aim. The the frequency is the one that has been given to us, and we have to meet this at any cost. We can't compromise on the frequency. It's 1 gigahertz and we have to meet it, and these are the parameters that you can tune to achieve to this one. So we have seen what happens when we when we keep on adding buffers on the launch flop clock path, and how it affects the left hand side of the equation. Now what we'll do is we'll take up one more case, and this is one more. If we add one more buffer over here with a delay of x, your data arrival time even increases even more. So there is a possibility of the slack going negative. Okay, now let us take one more case where we keep on adding buffers in the right hand side, or basically on the capture flop clock endpoint. So what happens when we do that? So let's say we add a buffer of delay x over here. So in that case, the data required time is increased. So basically it is expected to come at t plus delta 2 plus some minus some value. Now it is expected to come at t plus delta 2 minus some value plus an additional margin of x over here. So this is actually advantageous. If you see you're pushing this particular t to even more to the right hand side, so that increases this window for you, and that will help you to get a data arrival time which is much less than the complete data required time, including the x. So by adding delays in this particular path, you're actually pushing the clock to the right hand side. You're pushing the clock to this side, so that the window completely increases for this particular theta to be within this particular window. So this actually, you find it to be very encouraging and find it to be very advantageous, and you tend to do that even more. Let's say we'll add one more buffer, we'll push the clock even to the right hand side even more. We'll add one more buffer, we'll push the clock even to the right hand side even more, and we generate more and more windows for us. But we tend to see that this proving to be very, very much advantageous for us. But there is a point over here that we are tending to ignore, that what happens to the next stage. So what happens when this particular thing becomes the launch flop, and there is one more that becomes the capture flop. In that case, all this 3x delay will now become the data arrival time. So how is that? So for example, with this particular scenario, now this is the capture flop. Now there is one more flop which is present over here. So this becomes the launch and the other one becomes the capture. Okay, so now this 3x delay, which was the data required time in this case, becomes the data arrival time in the next stage. So in that case, what will happen? You're actually increasing the data arrival time. So you will be meeting timing for this path, but for the immediate next path, you are actually failing timing. You will be failing timing because the 3x becomes a required time for this stage, but for immediately the next stage, if there is a one more flop over here, this becomes the launch flop and this becomes the capture flop, and this 3x comes over here, and you actually lose on frequency on the other path. So you have to be very careful. So locally solving a problem is not the solution. You have to solve the problem globally. You have to look into the picture from a global point of view, how addition of these buffers, how addition of this clock buffers actually tune. So it's always better to have a skew of 0, which is delta 1 is equal to delta 2. If you have the clock network delay, if you have a launch clock delay, launch flop clock delay equal to capture clock flop delay, that is the best thing. That is the best thing that you can achieve. And so you might not get into this kind of issues where you have to push the clock, or you have to push the clock over here. You might not get into all those issues when you actually try to maintain a 0 skew. That's why we have focused on topics which will lead us to 0 skew in the clock tree synthesis network. So now what we'll do is, since I'm already running out of time, we'll take the same scenario where you're trying to add clock buffers in the launch clock path and the capture clock path, but not in the setup timing analysis anymore. Now we'll be doing a hold analysis with real clocks and with single clocks. So we'll look into a section where we'll be doing the hold analysis and how does the addition of this buffer that we just saw, for example, how the addition of buffers in the capture clock path and how the addition of the buffers in the launch clock path actually affects your hold analysis, and what are the advantages, what are the disadvantages, and so on. So let's try to look into all this from the next video. Thank you.